transform. And related to Fourier transform, in the previous class we have defined what is Fourier transform and what is the complex Fourier sine transform and what is the complex Fourier cosine transform. And also inversion formulas have been done. Some of the questions were done related to Fourier transform. Now today we shall continue with one or two results. The first result is convolution theorem. And, this is the important result we have, which we need to complete. The result is convolution theorem. Convolution theorem was also done in the chapter of a Laplace transform. In the Fourier transform, we again have convolution theorem. Now let us understand first what is the meaning of a convolution. Suppose we have two functions fx and gx. Then and these two functions are defined in the interval minus infinity to infinity. Then we can define the convolution of f and g, that is integral minus infinity to infinity f of u. The function is f of u g of x minus u du. This is the convolution of f and g. Now here, note it down, we are integrating with respect to u. So this is the meaning of a convolution of two functions. Now let us state the theorem. The theorem is the Fourier transform of f of x and g of x is the product. The Fourier transform of the convolution of f and g is a Fourier transform, and that will be equal to the product of the Fourier transform of f of x into the Fourier transform of g of x. So this is the statement of the theorem, and we shall prove the theorem by using the definition of convolution. So the Fourier transform of f of x convolution g of x. Note here, star is the convolution operation, and that will be Fourier transform of minus infinity to infinity. What is the definition of convolution? This one. This is f of u g of x minus u du. And now we can write down its Fourier transform. That is again minus infinity to infinity, and that will be minus infinity to infinity f of x g of x minus u du into e raised to power iota s x dx. This is by definition of a Fourier transform. Now, here it is integration with respect to u, and it is the integration with respect to x. It means first integration with respect to u, then integration with respect to x. But we shall change the order of integration. So by changing the order of integration, it can be written minus infinity to infinity. And that will be here the definition is f of u, not x. So this should be u, not x. This is f of u. So this f of u can be taken out, and inside of the bracket, that is minus infinity to infinity, u of x minus g of x minus u e raised to power iota sx dx, and this is the integration with respect to u. What we have done, we have just changed the order of integration. And in the next step, this is a minus infinity to infinity f of u. This will be as it is. We will write on minus infinity to infinity e raised to power iota s x. So in place of x, I am going to write on x minus u to d of x minus u into d of x. Now what extra term we have taken? E raised to power minus iota s u. This is the term which is extra we have adjusted over here. So you have to adjust the same term here so that its effect can be utilized. So the terms have been adjusted over here. So this is the integral minus infinity to infinity f of u. Now in the bracket term we have to use some operation. So you will substitute with x minus u is equal to some another variable t. So what it will come out to be minus infinity to infinity e raised to power iota s of t g of t, and clearly dx will also be equal to dt. You can find out the derivative here. This is the outside term. Now what is this? In the next step, this will be minus infinity to infinity. Now this e raised to power iota s u can be written over here with f of u, and this is the bracket term which can be written here e raised to power iota st gt and dt. And what is this? This du can also be taken over here. By definition of Fourier transform, this is the definition of Fourier transform of f of x, because we can change the variable, or we can also write it in this way also. First, we can change the variable. So it can be written minus infinity to infinity e raised to power iota s x f of x d of x minus infinity to infinity e raised to power iota s t. In place of t, you can change the variable x again, g of x d of x. Why you can change the variable? Because change of variable doesn't make any difference in definite integral. Now what is this? This is the definition of Fourier transform of f of x, and this is the definition of a Fourier transform of g of x. So you just see this is the multiplication over here. So this is the result of the convolution theorem, that the Fourier transform of fx convolution gx is equal to Fourier transform of fx into Fourier transform of gx. So this result is also very important as far as Fourier transform is concerned. Now, we have one more important result which is very much useful. This is a Parseval identity. That is Parseval's identity. Let us state the result. If the Fourier transform of f of x, we know that it is denoted by f of s, because Fourier transform of a function of x is always a function of parameter s. So Fourier transform of f of x is always a function of parameter s, and the Fourier transform of g of x is always a function of parameter s, that is g of s. Then we shall prove in the first part 1 upon 2 pi minus infinity to infinity uh, f of s. It should be f of s into g bar s into ds is minus infinity to infinity f of x into g bar x dx. This is the first part, and in the second part we shall prove 1 upon 2 pi minus infinity to infinity f of s square d of s is minus infinity to infinity f of x mod square d of x. You have to remember these parts of the Parseval identity. These are the parts of the Parseval identity. So we shall prove these results. Now in the proof we shall prove the first part, and the first part is minus infinity to infinity f of x g bar x dx. This is the left hand side, and in the left hand side this is minus infinity to infinity f of x. Now we just want to use the value of g bar x by inversion formula Fourier transform, that is the 1 upon 2 pi minus infinity to infinity g bar s e raised to power iota of s x into d of s dx. This is by the definition of inversion formula, and this will be 1 upon 2 pi. 1 upon 2 pi like a constant. So 1 upon 2 pi minus infinity to infinity. Now here the integration with respect to s, then with respect to x. So we will change the order of integration, and then it will become g bar s, and in the bracket it will be minus infinity to infinity f of x e raised to power delta s x dx. This technique or this criteria of changing the order of integration is very important in proving Parseval identity, this one, and in the previous result, convolution theorem. So that will be 1 upon 2 pi, and that will be minus infinity to infinity. This is g bar s, this one, and it can be written. What is this? This is the definition of f of s. It means to say Fourier transform of f of x. This is the formula for Fourier transform of f of x. I will write down the Fourier transform formula. Fourier transform of f of x is minus infinity to infinity e raised to power delta s x f of x dx. This is a Fourier transform, and you will know that this will be a function of parameter s. I already have defined this definition, and from this we can find out inversion formula. And the inversion formula is 1 upon 2 pi minus infinity to infinity. That will be f of s e raised to power minus delta sx dx. This is by inversion formula. In inversion formula, here comes a minus sign. But remember, we are writing down plus sign here because we are finding out the inversion. We are writing down the inversion formula for bar function. And the bar is always the complex conjugate. So that minus iota will be changed to plus iota. That's why plus iota is written over here. Otherwise, in the definition of inversion, this one, we always take minus iota ss. I am again repeating because this is a bar function, this one, g bar s, and we are writing down the inversion formula of a conjugate function. And the complex conjugate of minus iota will be plus of iota. That is why this has been digital program here. So this is the result. You just see the first part have been proved over here. Now we can prove the second part also. So proving the second part, we just take proving the second part, we will uh, take g of x is equal to f of x in this formula. And what will come out to be 1 upon 2 pi minus infinity to this is f of s. And now this is g bar s. If g of x is equal to f of x, then Fourier transform of g of x will be equal to Fourier transform of f of x. What does it mean? Meaning g of s will be equal to f of s. Or if we take the conjugate of that, then conjugate of g will be equal to conjugate of f. And in that case, g bar s will be same as f bar s. It's Fourier transform. So we can write down here that will be f bar s ds. And on the right hand side also minus infinity to infinity f bar x and f of x together. So we know the definition, this is always the modulus of that. So it can be written 1 upon 2 pi minus infinity to infinity, that is f of s mod square. Or that will be written like this, d of s minus infinity to infinity f of x modulus square. You know that modulus of f of s whole square will always be a positive modulus of f of s. So we can write down in brackets. So what will come out to be 1 upon 2 pi minus infinity to infinity f of s whole square d of s, that is minus infinity to infinity f of x square d of x. This is the second part of the Parseval identity. This is also very important. Now, with the help of these parts of Parseval identity, we can write down the Parseval identity for Fourier cosine transform and Fourier sine transform also. So in number one, the result will be 2 upon pi 0 to infinity FCS and GCS d of s will be 0 to infinity f of x g of x dx. This is the Parseval identity for Fourier cosine transform. Remember, this small c stands for cosine transform. In the similar way, we can write down the Fourier sine transform. Fourier sine transform, Fourier sine transform, and on the right hand side, the function will be same fx gx dx. So in the similar way as we have proved the part number one, you can prove these two results, number one and number two. Now, this number three is there, and in number three, that is 2 upon pi 0 to infinity. The result can be written like this also, as we have proved in part 2, that will be equal to 0 to infinity, that will be 0 to infinity f of x squared dx. So this is the cosine transform formula, and we can prove this result on the pattern of part 2. This one. So by using the technique which we have applied in part 2, you can prove. And you know that the proof of a part 2 is coming from the proof of part 1. Because in part 1 we are taking gx equal to f of x and its g bar x equal to f bar x. So we are able to prove. Similar way, we can prove the result for sine transform also, that will be 2 upon pi 0 to infinity Fourier sine transform square 0 to infinity, that is f of x square. So this is the fourth part. So these results are for Fourier sine transform and for Fourier sine transform. These are the parts of Parseval identity also. You can prove these results. So you must revise these results. You have to prove these results by using the first part and second part. This is your home assignment. You will prove the result. But remember, you will take a Fourier cosine transform for proving part 1 and Fourier sine transform for proving part 2. Formula will be as we have discussed in earlier classes. So I conclude here. We shall continue in the next class. Thank you very much.